Let's get started for today. The topic today will be Hilbert Spaces, but before we reach that point, I will remind you what we have done the last 2 weeks, and we also need a couple of steps before we introduce the Hilbert Spaces. So what have we done so far? So when I write last week, actually it means the last couple of weeks. So we have introduced normed vector spaces. This is what we did the first week. Then we moved on and considered Banach spaces. And actually, we do not need the exact definition today, so I will not write it on the board. But the way we defined Banach spaces was to require that all Cauchy sequences were convergent, that each Cauchy sequence would converge to something in the space. And we saw some examples of that. So we saw the space of continuous function on a bounded and closed interval. This is what we looked at already in the very first lecture. And then last week we took another step because we introduced a space that we did not know about before. Namely, we considered some p that was bigger than or equal to 1. And then we introduced the space LP of n. And we need that today, so let me write that. So this is the set of all sequences xk, where xk are just complex numbers, and then with the property that if you look at the sum of the absolute values of xk to the power p, then we get something that is finite. And it turns out that this space is a Banach space with respect to, and I'll just write that short, with respect to, and we need to tell what the norm should be. So the norm is something we will write as xk, and then with these parentheses around, and then we put a little p below the norm symbol because we use that norm so many times. And the way we define it is to take exactly this, but in order to get the norm axiom satisfied, we need to take the p root of that. So we take the sum xk to the power p, k equal to 1 to infinity, and then we take the p root of that. And actually, we have some even simpler examples of Banach spaces. So let me just write that as an example. What I want to state now is the space that you know very well, namely Rn. So let's look at some x that is in Rn. And in order to make the notation a little bit easier than I did last time, let me put a bar below the x, so it's clear for you that now we are speaking about a vector. So we will write it as x, and then equal to x1, x2, all the way to xn. And Rn is actually also a Banach space. And again, we have to say with respect to which norm. And actually, we could use all the norms that I have introduced here, but I just want to state one of the norms, namely what we call the 2 norm, the one where we take p equal to 2. So the norm of, and let me just write the x as x with a bar below. This will then be just the sum of xk to the power 2, k equal to 1 to n, and then we take the square root of that. So this is what you know already from Mathematics 1 or whatever course you had at the beginning of your education. The reason that I want to state this again is that if you think back about what you did at Mathematics 1 or whatever you had at that time, you also know that Rn has another concept associated to it. Namely, there's an inner product, a scalar product. So this is something I'll just remind you. So Rn has an additional structure, namely the structure of an inner product. And Some of you might not have called it inner product. Some of you might have used the word scalar product instead. And the way you define this is that you take the vector x with the bar below, and then you put a dot, and then you write another vector y, and the outcome of this is something that you have written as the sum from k equal to 1 to n of xk times yk. So you simply take the coordinates, multiply them together, and then make the sum over all coordinates. So this is something you know very well. The reason that I want to state this again is that you can see this is closely related to the norm. So what you see here is that if you take the inner product of a vector x with itself, then you get the sum of xk to the power 2, which is exactly what we have inside here. So in other words, you get the norm of x to the power 2. So this just says that the inner product between a vector and itself, this is equal to the length to the power 2 of that vector. Now, this inner product that you have on Rn, this is actually one of the main ingredients in the theory for Rn. It's one of the main ingredients in all linear algebra. It allows you to speak about orthogonality of vectors. So as soon as you have an inner product, you can speak about what does it mean that vectors are perpendicular to each other. So what we would like to do now is to take the step of generalizing the inner product from something that you know about on Rn, and now we want to do exactly the same on any vector space. So let's do that. So we'll make a generalization to arbitrary vector spaces. So let me define the concept for you. So the starting point is to choose any vector space. I would like to put an extra word here. I would like to say that it should be a complex vector space. So a complex vector space, this means that the scalars that you are multiplying on your vectors in the space, they might be complex. This is not the case for the space Rn. So Rn is not a complex vector space. Rn is a real vector space. So what I'll do is to write down the exact definition for complex vector spaces, and then after that I'll see if I can find some red chalk, and then I'll write here real, and then I state these few changes that are necessary in case we need to look at a real vector space. Most of the spaces we will speak about in this course are actually complex vector spaces. So all the new spaces I will introduce will be complex vector spaces. The only real vector space you'll meet is actually the Rn that we have down here. So a complex vector space, then we want to define an inner product. And we'll do it a little bit in a similar way to what we did as we introduced a norm. So we'll say an inner product, this is a mapping. So you remember, as I defined the norm, I was saying a norm is a mapping that to each element in the vector space associates a real number. So we'll do the same here. We need to find a name for this mapping, and the way it is denoted is by a little bracket that turns this way, and a little bracket that turns this way, and then we put two dots in the middle, and then a comma. So this is not a smiley face or anything like that. This just means that these are the places where you put in the variable. So you have two variables to put in, exactly like you have two variables to put in here. You have to put in an x and you have to put in a y. So what we are putting in here are elements. This should be something that belongs to V. This should be something that belongs to V. So it's a mapping that goes from V cross V in the sense that we have two variables in V, and then to each such pair we associate a complex number. And here you see the difference. The scalar product we have over there does not give us a complex number, it gives us a real number. So this is the difference between the complex and the real vector spaces, but I'll write that down in details later. So this is a mapping. But we want this mapping to act in the same way as the inner product we have here. That means we want this abstract mapping to have some of the same properties as we know from the inner product. So we will state some properties. The first property is that we actually have linearity with respect to what we put in the first variable. So that means if we put in some alpha v plus beta w, and then we take an inner product with some elements u, so that means alpha v plus beta w displays the role of what we're putting in here, and the u plays the role of what we're putting in here. Then we want this to be the same as just to take the alpha and then the inner product of the v with the u, plus, and then we take the beta, and then we take the inner product between w and u. So what this actually says is we want the inner product to be linear. It should be a linear function of what goes on in the first variable. So we want this to happen for all choices of these vectors v, w, and u. So for all of them belonging to v, and we also want it to happen for all alpha and beta belonging to the complex numbers. The second one is a little bit easier. It says that if you look at the inner product between v and w, then, you know, if you look again at this situation, whether you take inner product of x with y or you take y with x, this will give you exactly the same number. So you can exchange the order of x and y if you want, because here you just exchange two numbers that you're multiplying, so this does not make any difference. Here, in the setting of complex numbers, this is different. So what we require is that this is the same as when we take it in the opposite order, but then we take a complex conjugate on that. So this is a change compared to what you know already. This is actually point 2. The third one is not something you have really thought about in the setting of Rn, but we'll see the role of it very soon. So what it says is that the inner product of v with itself, this is always a positive number. This is of course a property that you know from this situation because the inner product is equal to xk times xk and then the sum, which is equal to the expression we have here. So we know that we get a number that is greater than or equal to 0, but we do not know why this is so important. But here we put this as one of the conditions. And we also want, maybe I should say, we want this for all v in the space, and that the inner product is equal to 0. This is exactly the same as v being 0. So these are the conditions that we will put on an inner product. And I have more or less already given you the first example of that. So Rn would be the first example. So Rn, we do exactly what we're used to. And then we look at this definition and we check that all these properties are satisfied. I will not do that. What I'll do instead is to look at the complex case, because this is what is new for you. So Cn is also a vector space with an inner product. And then I need to tell you what is this inner product. And the way we define it is x, y, and we take almost the same as what we have here, except that we put a bar on the yk. So let's check that this actually satisfies all the conditions that we have here. So let's call it a proof, but we only look at it for the case of Cn. So you can see the situation is very similar to what we had as we looked at normed vector spaces. Normed vector spaces, we also had a condition 1, 2, and 3, and we actually had something else that we should check before we started the proof. Namely, you see here, we need to check that we actually have a mapping from V cross V into the complex numbers. This is the first to look at. So this is satisfied here. If we call this condition for somehow the condition 0, because this is not stated among the 1, 2, and 3, then we just look at what we have here. We look at the definition of X inner product with Y, and then you see all what we have here is a product and a sum of some complex numbers. So what comes out here will be a complex numbers. So this is something that belongs to C. So this is the first part to check. So now we have to go through 1, 2, 3. So let's take them one by one. So let's look at the linearity. So this is alpha V plus beta W inner product with U. Now where we're dealing with sequences, I think the natural notation would be to say alpha times the vector X plus beta times the vector Y inner product with some vector C. So let's look at this. So the definition that is stated here says that this means we are looking at a sum starting from k equal to 1 to n, and then we have to take the kth component of the first vector. And the kth component of this is just the alpha times the xk plus the beta times the yk. So we have to take this and multiply with the kth component here, where we remember that everything in the second coordinate should be complex conjugated. That means we are looking at ck complex conjugated. And then you look at this and you say, this is just a finite sum of some numbers, so we can manipulate with this exactly like we're used to. So you see, here you can actually split it in something that has to do with alpha xk, ck complex conjugated, and something that has to do with this and that. So the first term will be this times ck complex conjugated. Here the alpha does not depend on k, so this is something we can take out. So this is the same as alpha, and then the sum k equal to 1 to n, xk, ck complex conjugated. And for the second term we get the beta times the sum k equal to 1 to n, and then we get yk, ck complex conjugated. And if you look at this, this is exactly the alpha times what we have here by the definition. This is simply the inner product between x and c. And then we get plus beta, and what we have here is exactly the inner product between y and c. So that means this verifies the first condition. The second condition means that we look at the inner product between two elements. Let's just now call them inner product between x and y. So again, if you look at the definition, we just take it from here. So this is the sum k equal to 1 to n, xk, yk, complex conjugated. And we want to manipulate with this such that we get something where the y is in the first coordinate and the x is in the second coordinate. And the way to do that is simply to put a big bar over everything and then look at what is inside here. So if you have a big bar over everything, we don't need to conjugate the yk, and I can even change the order if I want, because these are just complex numbers. So this is yk, and then I want something that has to do with xk. So if I just write xk, it is not correct, because the xk will then get conjugated here, which is not what we have here. But if you take the complex conjugated inside this, then we take the conjugated of xk and we conjugate it one more time. And this will give you the xk back. So this is exactly the same as what we have here. And if you look at what is inside here, this is exactly the inner product between the y and the x. So this is what is inside here, and then we have a complex conjugation on everything. So you see, now you can change the order, and the price to pay is that you have to put a complex conjugation on everything. So this is okay as well. Now, you might actually have wondered, why did I choose to put this complex conjugation here? But you can see that now, because when we look at the third condition, we need to look at the inner product of an element with itself. So let's look at x inner product with x. And by this definition, this is then what you see you get here is xk times xk complex conjugated, which is exactly the absolute value of xk to the power 2. So you only get that this is positive because the definition of the inner product actually has this complex conjugation on the second entrance. So this shows that we have the first property, and then we need to show what does it mean that it is equal to 0. And then we just look at it and say, it is given by this expression, and this is a sum over non-negative numbers. So this being equal to 0 is exactly the same as to say that xk is equal to 0 for all k. And xk being equal to 0 for all k, this is the same as to say that x is simply the 0 vector. So this verifies the third condition that we had here. So that means we have indeed that Cn is a complex vector space and that this defines an inner product on the space. Let's do a small change compared to what we are doing in the definition. So if you're looking at the definition here, you see the linear combination is in the first coordinate. What happens if you put the linear combination in the second coordinate instead? So in other words, what happens if you're looking at an inner product between, and now we go back to just the setting of abstract vector spaces, we look at the inner product between V and some alpha W plus beta U. So can any of you tell me, how can we get an expression for that? Alexandra?
We can use the combination of 1 and 2. So first we take the conjugation, so we swap them, and then we...
You swap them, yeah. Yes. Because then you have the linear combination in the first entrance. And then you can use the first one. So let's do that, but let's do it quite fast. So you say we swap them, so we get the alpha W plus beta U, and then the V. And then the price to pay is that you have a complex conjugation on this. Now the idea is that when the linear combination is in the first entrance, we can use the first rule to split it by linearity. So this is the same as alpha, and then we have W with V plus beta, and then we have U with V, and then we have a complex conjugation on everything here. So what comes out is that the complex conjugation on everything will go down to be a complex conjugation on the alpha, and then we have a complex conjugation on WV, but then we can just remove that complex conjugate again by swapping the order again. So then we get V and we get W. And for the second term, exactly the same happens. So we get the beta complex conjugated, and then we get UV complex conjugated, and then again we swap the order and we remove the complex conjugation. So this is then V with U. So you see, this is dangerous. This is really a point where you have to be careful, because intuitively, if we didn't look carefully at the definition, you'll probably say that it does not matter whether we have this linear combination in the first entrance or in the second entrance. But what you see here is that if you have the linear combination in the second entrance, you can still split it out using some kind of linearity, but you have to remember to complex conjugate all the coefficients that are coming out. So remember that. Okay, let's again look at something that you know. So the way we will develop the theory is actually to play pinpoint with what you know and what is new. So we always go back and look at something you know, and then we move it to the new setting. So we have been speaking about Rn, but let's speak about R2. So in R2, what does it mean to have an inner product in R2? This means that you have a vector x that is sitting here, and you have a vector y that is sitting here, and you have an angle between these two vectors. Then you know that the inner product x, y, this is actually the same as the length of the vector x times the length of y times cosine to the angle theta. So this is probably something you saw already in high school. So what this means is that if you're looking at the absolute value of the inner product, then this is equal to the length of x times the length of y times the absolute value of the cosine. And the absolute value of the cosine is at most equal to 1. So in other words, this absolute value is smaller than or equal to just the length of x times the length of y. Which, if you write this in terms of the inner product, then this is the same as just the inner product of x with x to the power a half. So you see, this is what you get from what we already wrote down here. So you can relate the inner product at the length of the vectors. And in the similar way, this is just the inner product of y with y to the power a half. So this inequality, that the absolute value of an inner product is smaller than or equal to this, is something that we can also state in general vector spaces. And actually, if you take the proof of this and you look at it in the setting of Rn, then exactly the same proof can actually be used in arbitrary vector spaces. Because if you go and look at the proof, then you will see that the rules that have been used again and again in the proof are exactly the ones that are stated here. So I will not go through this proof, because this is something that you can actually go back to your e-notes from Mathematics 1, and then you can just see how to prove these steps. And you can see that it's exactly the same we have to do here. So the similar result in vector spaces. This is formulated in the book as a theorem. And this is something that you will use repeatedly in this course. It actually has the name Cauchy-Schwarz inequality. So what it says is that if you're looking at an inner product between V and W, and you look at it in absolute value, then this is smaller than or equal to the inner product between V and itself to the power 2 times the inner product between W and W to the power a half. So I will not prove this because the proof is the same, but I will show you how we can apply this to connect the norm and the inner product. So it actually turns out that no matter which vector space you're looking at, as soon as you have a complex inner product, then you can actually define a norm on that space. And that means that the setting of spaces with inner products is actually a subsetting of what we looked at in the very first lecture, namely the vector spaces with a norm. So this is a very important observation, so I'll give you the full proof for that. So let's formulate the result first. So what it says is that if you have a vector space with an inner product so we take the inner product and we denote it by this triangle notation, then we actually automatically have a norm on the space. So we can define the norm, and the way we do it is exactly like we did here. So the norm should be defined by taking the inner product of an element with itself and then take the square root of that. So let's see how we can prove this. So I think it's most convenient that we have the definition of a norm to look at. So what we have to do is to, again, you see, we have 3 points to discuss, but we have the extra point that up here in the proof for Cn, you see I introduced this point 0, and the point 0 is also something we have in the definition of a norm, because this is that a norm should be a mapping from the vector space into the real number. So this is something we always need to remember to check. So we check these 3 conditions, but we also check that the norm actually maps the space into the real numbers. So again, if we call this point 0, then we need to look at this and we need to check that this belongs to R. And the reason that this belongs to R, this is because this is the way we have defined it. You see, it is a positive number or maybe 0. So this is a consequence of 3. So this is okay. So let's go through the points 1, 2, and 3 here. So let's look at the first one. We need to show that V, the norm of V, is greater than or equal to 0. But the norm of V, this is just the inner product between V and V to the power a half. And again, if you look at this, then this is positive. So this is okay. And what does it mean that the norm is equal to 0? This means that this is equal to 0. And by the condition that we have here, this is the same as to say that V is equal to 0. So both these conclusions are by using the definition 4, 1, 1, and then simply the first part. Then let's look at the second one. Alpha V, we need to look at this in norm, and then we need to show, according to what we have on the slide, we need to show that this is the same as the absolute value of alpha times the norm of the V. And the only way we can do that is to use the definition of the norm. And the definition of the norm says that then we have to put in the vectors and take the square root in the inner product. So this is alpha V, and then to the power a half. So we want somehow to get the alpha out. And for this alpha, there's no problem. We can just take it out because this is what the first condition tells us that this is allowed. Alpha in the first coordinate can always be taken out. So this alpha goes out without any problem. What about the second alpha? This is sitting in the second entrance of the inner product. So the calculation we just did shows us that whatever we have here can also go out, but we need to put a complex conjugation on that. So this comes out as alpha with a complex conjugation. And then what is left is the inner product with V and itself. And then take the square root of this. Alpha times alpha complex conjugated. This is the same as alpha to the absolute value to the power 2. And what we have here, the inner product with V and itself, this is, according to this will be the same as V to the power 2. So we need to take the square root of this. And then you can see, you take the square root of all this, what comes out is the alpha times the length of the V. So this follows from our definition of the inner product. What about the third one? So in the third one, this is the triangle inequality. So we need to look at the norm of V plus W, and we need to show that this is smaller than or equal to the norm of V plus the norm of W. It turns out that instead of working with this as I state here, it is better to work with it to the power 2, because then we avoid to put the square root all the time. You see here, I had to run around with the square root all the time. So in order to avoid that, let's look at this to the power 2 and make the calculation for that. And then after that, we can always take the square root. So the norm of this to the power 2, again, according to the definition, this would be the inner product of the vector with itself. So this is the inner product of V plus W, V plus W. And now, you see you have a linear combination in the first entrance. So you can use, again, the first property we have here to split it out as two inner products. So you can say this is the inner product of V with V plus W plus the inner product with W and then V plus W. And now you are left with something where you have a linear combination in the second entrance, but the coefficient is 1 times V plus 1 times W. These numbers are real, they are not complex. So this means that we can split further here, so we can say this is the same as just the linear combination. I'll actually write it here. This is the V inner product with V, this one with this one, and then the inner product with V and W. And then we split this in the same way, so this is W inner product with V plus W inner product with W. Now, what we are calculating here is something that is greater than or equal to 0. Because this is what we observed already here, that the norm of any vector will always be bigger than or equal to 0. So all what I have written down here is greater than or equal to 0. So this means that if I want, I can put an absolute value here. It does not change anything. But it is a very good idea to put this absolute value, because we have something called the triangle inequality that says that if you take the absolute value on a sum of a lot of terms, this is smaller than or equal to what we get by taking the absolute value of the first plus absolute value of the second plus, and so on. So all we have here is smaller than or equal to absolute value V with V plus V with W plus W with V plus W with W. And this is something we can estimate. The first one is the inner product of V with itself. Again, by the definition of the norm, this is the same as norm of V to the power 2. This inner product, we don't know what it is, but Cauchy-Schwarz tells us that this is smaller than or equal to V, the norm of V times the norm of W. Because you see what we have here, we get the inner product of V with itself to the power 2. This is exactly the definition of the norm of V, and this is exactly the definition of the norm of W. So this is what we get for this term. If you look at this, we get exactly the same, we just get it in the opposite order, but we still get just the norm of V times the norm of W. So actually, at the end of the day, we get this, but we get it with a factor of 2. And then we have this term, and this is norm of W to the power 2. And then we do something that you did in high school, but of course you don't recognize it here because of all these strange symbols. But what you have here is exactly the same as the norm of V plus the norm of W, all of it to the power 2. Because this to the power 2 means this to the power 2 plus this to the power 2. This will give us these terms, and then 2 times this times that. And this is exactly what we have in the middle. So that means all these manipulations have given us that the norm of this to the power 2 is smaller than or equal to this to the power 2. And then we just take the square root of everything. So this gives us that the norm of v plus w is smaller than or equal to the norm of v plus the norm of w. And this is exactly the third condition that we wanted to check. We wanted to check the triangle inequality that we have here. So using all these manipulations, we have actually done that. So I think by now you must be convinced that this is a good definition of an inner product, because the definition we have here play very well together with the definition of the norm that we already have. Now I promised to do something for you, and before I forget it, let me see if I can find some red chalk so we can note how the definition of the inner product needs to be changed if you look at real spaces. So maybe the blue is the best one. So what happens if this turns out to be a real vector space? So let's just mark it here. No, this is not good. I can see that on the board. So let's take the orange instead. So what happens if we are dealing with a real vector space instead? Then an inner product will still be a mapping that takes a couple of vectors and maps it to some numbers, but in that case we want the outcome to be a real number instead of a complex number. And this also means that when we are looking at linear combinations, when we have a real vector space, this means that the coefficients alpha and beta are real numbers instead of complex numbers. So here we need to change and say we put in real numbers instead. But besides this, this is just linearity, so the definition as such is the same. Now here, since this is a real number, whether we make the complex conjugation or not does not change anything. So in the real case, this will just be equal to the inner product WV. So we simply remove the bar in the real case. The last part of the definition is exactly the same. So you see there are these minor changes, and you just need to pay attention to whether you're dealing with a real vector space or a complex vector space. And as I say, all the vector spaces we're dealing with in this course are actually complex vector spaces. So this is just made in order to really to make Rn be a special case of what we're doing here. Now, before we take the break, I would like to show you a very important statement about the inner product spaces. So the key result in this section is actually the one that has the name Theorem 4.14. That comes right after what we have discussed so far. So the question is, how much is new here and how much do we already know? So you see it has 4 points, and if you look at the first one, this is exactly the Cauchy-Schwarz inequality. So this is exactly the one that we already stated, and I think I took it away already. We needed the space. But there's no change. This is exactly the Cauchy-Schwarz that we already looked at. So the new part is from 2 down to 0.5. So all these are new. And all of them will be something that you will prove during the exercises. Not all of them today, but during today and during some homework and during next week, I think we will get through all the proofs of these statements. Let's look at the first one. Let's look at the 3.4 first. Let's do it here. So we write down some comments to Theorem 4.14. So let's look at the point 3 and 4. So you can see what they do is to relate the norm and the inner product. So what they show, for example, if you look at 4, this is in the case we have a real vector space. What it says is, if you can calculate all the norms that are stated here, then we can actually calculate the inner product of V and W. So that means if you know the norms of all vectors, then you can actually calculate back and you can find the inner product. If you look at 3, this is exactly the same. If you can calculate all the norms that are stated here, then you also know the inner product between V and W. So what this says is that you can actually recover the inner product if you know all the norms. So if you think about this, this is exactly the opposite of what we did so far. So what we did so far was to say, let's take the inner product and then we define our norm. Can you see? This is what happened here in the very first line. We start with an inner product and then we define the norm by the inner product. So if you have the inner product, we know how the norm is by definition. And the statements that we have here, point 3 and point 4, tells us that we can also go back. If you know the norm, then we can go back and tell what the inner product is. There's one more of them that I would like to say just a few words about, and that's point 2, the parallelogram rule. So it turns out that there are many vector spaces where you don't have an inner product. We have just defined vector spaces with inner product, but there are a lot of norm vector spaces where you don't have an inner product. So what this tells us is that the definition we have here, this is a very nice definition when it is satisfied. But there are many cases where these conditions do not work. We cannot make an inner product that will help us. But what the theorem tells us is that if we have a case where there is a norm coming from an inner product, then we actually need to have the parallelogram law satisfied. So that means if you are in a case where you have a norm on the space, and you do some calculations and it turns out that the parallelogram law is not satisfied, then you know that the norm does not come from an inner product. So the role of this is that if the parallelogram rule if this is not satisfied, then actually the norm we are dealing with does not come from an inner product. And this comment is something that would be helpful for you when you make your homework, because it turns out you have 2 exercises that are called 4, 5, and 6, 2. And in these exercises, you actually use exactly this observation. So please remember that. I don't know if you have any questions, or if not, yes, you have a question?
Does that comment, the first comment, does it apply to any norm we create?
This one?
Or only, yeah. Or does it only apply to the norm we create from the inner product?
You see, the assumption in the theorem is that you look at a vector space that has an inner product, and then you have the associated norm. So it is about a norm that comes from an inner product. So let's take our break now, and let's say that we're back in the usual time, about 12 minutes, something like that.